In this paper, we studied three-dimension-aware image attribute editing problem. We have three keywords in our goals: a single image, precise, and real-time. To achieve our goals, we train a nerve-based gain inversion encoder and perform latent space manipulation to achieve semantic editing, such as smiling and wearing eyeglasses. Our key point is how to train the inversion encoder and how to improve the precision of the editing. Here are some results. Our method enables reconstruction texture and geometry from a single image and allows one to perform a list of attributes, editing sequentially. Neural readings field models the underlying three-dimension scene through a continuous five-dimensional function, f theta, that maps the position and the view direction to color and corresponding density. Multi-view images are then obtained using volume rendering techniques. Some works are combining NERF and the GAN framework to generate multi-view images from the latent code. The state-of-the-art model is EG3D. The GAN inversion is a reverse process that finds out the latent code of an input image. This latent code can be used to reconstruct the input image through the generator. Existing GAN inversion methods can be grouped into three categories: optimization-based, encoder-based, and hybrid both. Many works have explored the GAN latent space of semantic manipulations. Some are supervised methods, and some are unsupervised methods. The common approach is to seek the editing direction responsible for controlling a given attribute, such as ending a smile or decreasing age. In this paper, we introduce an encoder mapping a single real image to the latent space W+, and suggest performing image editing in the inversion manifold. Our method is based on a pre-trained three-dimension generator. The generator can synthesize multi-view images conditioned on camera parameter C. We train an encoder E to invert the given image to the latent code W and perform latent space manipulation to achieve semantic editing. To improve three-dimension consistency of the encoder, we explicitly encourage three-dimension consistency during training in two ways: alternating training scheme and multi-view identity loss. The alternating training scheme consists of in-domain iteration and out-domain iteration. The model takes in a batch of out-domain images, followed by a batch of in-domain images. The encoder is optimized to reconstruct the input images when inverting the out-domain images. When inverting the in-domain images, we additionally optimize the encoder to reconstruct the latent because we have the ground truth. To improve the identity similarity between images with different poses, we propose a novel loss, L multi-ID, including two terms: the identity loss and the original camera pose, and the average identity loss and the surrounding camera pose. The total losses also include L2 distance and the perceptual distance. We refer to the spaces used for generated images and the original latent spaces of the generator, denoted as W+ origin. Instead, we propose that the space consisting of latent codes obtained by inverting a large number of real images, where an inversion encoder is called inversion manifold, denoted as W plus inversion. It turns out that there is a distortion between W plus inversion and W plus origin. Because we use a latent code W to generate an image, but we can't get the same latent code when inverting this image. Therefore, editing the latent code in W plus inversion with the editing direction found in W plus origin leads to distortion. So what to do? It's simple. We seek the editing direction in the inversion manifold and use them to edit the inverted latent code. Well, let's see the results. ID metric indicates if it is the same person. APD indicates the error in the pulse of a generated image. AA indicates the change of the attribute we want. AD indicates the change of other attributes that we don't want. The results of inversion and editing both show our method outperforms the previous method. Similarly, editing in the inversion manifold of two-dimension GAN also achieves better results than in the original latent space. Here are some visual results. This is increasing age. This is wearing eyeglasses. This is smiling. This is wearing a goatee. This is waving hair. The last is a demonstration of interactive editing. After we upload an image, we get the three-dimension reconstruction result, and we can make him stop smiling, turn his hair color to black, put eyeglasses on his face, and let him grow a goatee. The important thing is that we can change the pose at will.